Good morning, everyone. This is International Marketing class, and the topic we are discussing today, it's also related to global strategy, international management, and the topic is complex multinational projects. And within that, we will be discussing James Webb or Webb Telescope, which will be launched in December, on December 18, and it is a truly mega project. How big? $10 billion. $10 billion. Imagine. According to the GAO, most of the projects which are 250 billion, they come under large scale. But mega projects go beyond 1 billion. So this is truly a mega project, and it's very important that we understand what's going on in the world, because this telescope, space telescope, is going to break all the records, and it is 10 times bigger than, and in terms of its resolution and all these things, Professor David Craig will talk about it. But I'm going to say a few things after that we get to our main seminar. So I have my cell phone here, and when I look at this cell phone, it says James Webb Space Telescope, 51 days to go. 51 days, 20 hours, and 8 minutes. This is my cell telephone. So basically, December 18. And the issue behind big projects, they are very big. How big? Most of those are billion plus. It takes a lot of time, and they are truly multinational. Means that more than 15 countries are involved in the James Webb. 15 countries, and 300 plus institutes, universities, research organizations, private contractors, everybody. Very, very complex. There are 3 delays in the launch. Hopefully, it will be taking off on 18th, but our guest speaker will tell the details. It's going to go too far, 1 million miles away. And this is where our whole program is. And if you look at complex multinational projects, in these days, as we are discussing in our class, we are dealing with the globalization of markets. Global strategies are all in front of us, and some global strategies become grand strategies, truly grand strategies. So we live in a global world, and our speaker is an expert in radio astronomy. That's his background. And overall, I want to show you, this is National Geographic. This is National Geographic March 2019. And it has a special segment, and I'm going to read from the magazine. It says, we are not alone. We are not alone. And it has been discussed all over the world for many, many, many years. Okay? Scientists say that there must be other life in the universe. Here is how they are searching for it. So James Webb Telescope is going to be one of the strategies. But behind James Webb, when you build a telescope like this big, a lot of people, it is not only scientists, it's also including business people. It's also including multinational teams. People are sitting in Europe because it's a collection of European Space Agency, NASA, and Canadian Space Agency. So this is where we call it complex multinational. It's not easy. It is very, very time consuming. And other issues, very quickly, I want to talk about it, and that is mega projects, as I said before very big. What are the examples of mega project? Hoover Dam. And then we have annual airports, okay, roads, and R&D, research and development. I mean, you can name anything. As long as it goes below 1 billion, then it's a large scale, but beyond 1 billion. So these are the issues. But the other thing is about this James Webb, and I'm going to read, and it has been discussed in many magazines, and that is, it's going to unveil the mysteries of the universe. I mean, just wait after December. It will take about 5 to 6 months to get into its operations, But if successfully launched and redeployed, which Professor Craig will let you know, it will create revolutionary issues. Okay, Hubble is kind of an old horse now. It's 34 years old. And this is where James Webb or Webb Telescope, when it comes in, and my comment is, after that I will move to our speaker. Humanity's premium observatory, and basically it is so big that it's mind-boggling. So this is where our talk is, but overall, at this time, let's give a warm welcome to our friend, Professor Craig.
Thank you. Thank you. Okay, so let me get my PowerPoint started here. The usual thing. There we go. So again, I'm going to talk about this as a complex multinational project. I'm mainly going to talk about the scientific justification of the telescope just in general, and about how it's deployed and launched, and kind of give you an idea of kind of the scale of the whole project, because this is the largest in terms of aperture space telescope ever launched. It is also mechanically very complex, and I want to talk a little bit about some of the difficulties and possible problems as we go along. So the first thing I want to talk about is why we use space telescopes. So some of you, I see at least one person who's been in my astronomy class. One of the things to realize is that we live under an ocean of air. Okay, we are on the Earth. The Earth's atmosphere is only transparent in a couple of regions of the spectrum, basically in the visible light that we see with our eyes, and in radio waves, and some of the shorter radio waves that we often call microwaves. The James Webb Space Telescope is designed to work in parts of the spectrum where our atmosphere is both absorbs light, so it's actually opaque, and glows to its own temperature. So in this room, we're at about 300 degrees Kelvin above absolute zero. We're all glowing by our body heat. Each one of you is putting out about 90 watts of body heat, and that comes out as infrared radiation. And the wavelength ranges that you see with your eye, and I've picked these units just to match up with the ones in a lot of the literature about the Webb Space Telescope. You see wavelengths from about 0.4 to 0.7 micrometers. That's from blue or violet light to red light. The Hubble Space Telescope can cover a little wider band because it's in orbit, and it has cameras that go to what's called the near ultraviolet and the near infrared, and that covers a wavelength range of about 0.2 to 2.5 micrometers. James Webb's telescope is designed to cover a region from the orange light that you can see with your unaided eye out to about 25 microns. 28.3 microns. The other thing to realize that's kind of a change, one of the reasons that it was chosen to build an infrared telescope is since Hubble was originally launched, the technology for ground-based telescopes in the visible spectrum in particular has really advanced. And it's now possible in many cases to remove some of the blurring in the atmosphere that occurs in visible light. You can actually send shine a laser beam into the upper atmosphere and excite. One of the techniques they use is to excite sodium atoms in the upper atmosphere, and then look at that and determine how the atmosphere is blurring your image and correct it. And so large visible light telescopes are now capable of many of the capabilities of Hubble Space Telescope, though not quite all. So on the other hand, with infrared light, Earth's atmosphere is basically opaque. I mean, there are a few small windows, and it's of a great deal of interest in astronomy. There have been several other infrared satellites launched, but this will be by far the largest. So here's just a little graphic to give you an idea of the spectrum. You can see these are the windows in our atmosphere, and this is wavelengths along the bottom in a scale that goes up by a factor of 10 for every tick mark. And so most of the shorter wavelengths, nearly all the shorter wavelengths and many of the longer wavelengths of light are blocked by Earth's atmosphere. And this satellite represented right here is one of the earlier, smaller infrared telescopes that's been launched and is actually still operating at a reduced capacity. It's called Spitzer. And so that's where this graphic came from, but it shows that most of the infrared spectrum is absorbed by our atmosphere and essentially blocked by the atmospheric gases. Here's I always like to show a fun picture. Here is, again, the little dog, and you can see the dog is glowing in the infrared. This is from an infrared camera on the ground. His fur is insulating, and so you can see there is less, in the case of this dog, there is less infrared light coming out where he's furry and more where his mouth is open and where his eyeballs are glowing because they're warmed by his internal body heat. If you see a similar picture of this of a person, you'll actually notice since we aren't as furry, we actually emanate a fair amount from our skin, and our eyeballs are actually a little cooler than our skin. But for this little dog, you can really see that. The infrared also has a lot of important properties in astronomy. These are both pictures from Hubble Space Telescope. The one on the left is using the visible light cameras of Hubble Space Telescope. And you can see these are dust clouds in what's called the Carina Nebula. The scale of this picture is probably a few light years across. So this is actually, for instance, our solar system would probably fit in one of these little fingers on the edge of this cloud. If you look at it with infrared light, you can see that the dust becomes much more transparent. You can see stars in the background. You can see details inside the cloud. And this is just one of many examples of how infrared light is different in astronomy from visible light. And so James Webb is going to be by far the largest infrared telescope ever deployed in space. It's actually of a size comparable to large research telescopes that are used on the ground, with all the disadvantages that that has. So here's kind of an overview of the launch in the telescope. It's planned to be launched on an Ariane 5 booster from French Guiana on the northern coast of South America, as we mentioned, in December. The Ariane 5 booster is a very reliable heavy lift booster developed by the European Space Agency. It is packed in this canister up here, all folded up. But as you look at this picture, one of the things to remember is that's a rocket that takes off mainly with solid fuel boosters. These two things are solid fuel boosters. They're going to be extremely powerful and produce a great deal of vibration. Then it has a liquid rocket that acts sort of as the throttle and to carry, as part of the first stage, to carry it higher into orbit. One of the things to realize about, and really the most important thing to realize about why space travel is so expensive, is the initial speeds required. To get a spacecraft to the position where it's eventually going to reach the near Earth's surface, or in low Earth orbit, the spacecraft will have to be up to a speed of something like 7 miles per second. So think about that just a second. It's 23 to 25 times faster than the speed of sound at the ground. Any rocket that is launched like this, 90% of the mass of the rocket on the pad is fuel. Okay, and so basically you're going to put a large, expensive object on top of something like 1 million pounds of explosive and fling it into the sky. So that's why you have to be very careful, and that's why it's stupendously expensive per pound to launch something into either a high Earth orbit or an escape orbit, which is essentially the orbit for this spacecraft is beyond the moon. It's essentially an escape orbit from the Earth. So here's the position. It's an interesting place to put spacecraft is called L2. It is 1.5 million kilometers beyond the Earth in the Earth's orbit around the sun. It is a special gravitational point where it will sort of be towed along by the Earth's gravity as it orbits the sun, as the Earth and the spacecraft orbit the sun. And that will give it a situation where the Earth and the moon are always between it and the sun. The Earth and the moon will always be essentially almost in one direction, so it's easy to point an antenna. And this spacecraft uses a passive heat shield to cool the telescope and all the electronics. And so that way the heat shield can basically face almost in one direction and keep the rest of the spacecraft in shadow at all times. So those are several of the reasons this orbit was chosen. There have been several other research satellites placed at this orbit, but this again will be by far the largest. So it is what's called a halo orbit. It's actually not going to sit exactly at that point. It will orbit around that. As I just mentioned, sometimes I do this, I say my slides before I get to them. It keeps the Earth, the moon, and sun always on one side of the spacecraft. It allows passive cooling with the heat shield, and it is beyond the current reach of any manned system for repair. Basically, once it gets out there, we, at the moment, do not have a spacecraft capable of taking, say, a human crew out there to do anything if the telescope doesn't deploy properly. However, interestingly, they did include on the design of the spacecraft grapple rings for other spacecraft to attach to it. And that's partly a lesson from Hubble, in that it was not expected when Hubble was launched that it would ever need to be repaired, but it actually needed to be repaired within a couple of years. Actually, they got up there as fast as they could because of a manufacturing flaw. And so since then, even though we're not certain that any crewed mission could get there, it also might be possibly serviced by a robotic spacecraft. So they have included at least some provision for grappling something to it. So now I will try to show you this nice animation of how the orbit works. This is pretty brief. So again, the L2 point is what's called a metastable, or one term for it's a metastable point. The spacecraft is going to basically orbit relative to the Earth in a halo around that point. But actually, all these bodies are orbiting the sun, the Earth, the moon, and the spacecraft. And so let me actually go back and play that one more time just for a second. So you can see from this view, this is showing the geometry. Everything's not to scale, but it's just showing you the basic geometry of where it will be. And one of the limitations of this type of orbit is it's not entirely stable. It's very convenient for this type of spacecraft, but it takes a small amount of propellant, in other words, a little rocket engine on the spacecraft with a fuel tank to maintain that orbit. And that is rather different from Hubble. Hubble basically needs almost no, I believe it probably has a few consumable, small maneuver rocket on it, but it doesn't really need any consumable supplies. JWST does, and so it actually has a limited lifetime, a more limited lifetime than Hubble. The riskiest thing about this mission, at least in my opinion, and I think generally that's the consensus about it, is the mechanical deployment of the spacecraft is pretty complex. It has to deploy without other mechanical help on its way out to its final position. You have to unfold the heat shield, the communications antenna, the mirror sections, and the secondary mirror, which actually sends the light path back into the main instruments of the telescope. So again, it's going to take about a month to reach its final more or less stable orbit. On the way out, it's going to successively deploy these various mechanical parts, and actually I'll show you an animation of that from Northrop Grumman was the primary contractor for the spacecraft itself. And so here is an animation of a few minutes. While they do this, I'll make some comments as it goes along because it doesn't have a narration. So just about 40 minutes after launch, or 30 minutes after launch, the first thing, of course, is to get the spacecraft stabilized, and then it will put out a solar panel to provide electrical power for the spacecraft for the rest of the mission. Now, one of the things to realize is it starts off from the Earth at a very high speed, but as it climbs away in the Earth's gravitational field, it will gradually slow down. So it's actually going to be moving slower and slower as it gets closer and closer to its final position relative to the Earth. There's some navigation that has to be done. At various times in the flight, there are small rockets built into the spacecraft that will slightly change its speed to correct for its final orbit. So about a day out, the high gain antenna, so this is the antenna that's capable of a high data rate to transmit the data back to Earth, will be deployed. Every time it says mid-course correction, that's going to be a rocket firing of the small rockets on the spacecraft. It'll pass the moon and the Apollo manned flight record, which was Apollo 13. And then after about 3 days, which is just about the time it will pass the moon, it's going to begin deployment of the sun shield. And so this is basically, in space, you're in a vacuum. And if you can put something in shadow and reflect any heat coming through through the material that makes that shadow, you can get things on the shadow side extremely cold by just letting them cool to space itself. And so once this heat shield is deployed and then it stays out there for a couple of weeks or more, the temperature of the spacecraft is going to drop to only about 50 degrees above absolute zero. And that's very important for it being an infrared telescope, because any temperature above absolute zero produces a little bit of infrared radiation, and to have your camera have maximum sensitivity, all the mirror elements going into your camera need to be cooled, and the camera itself can be cooled. And in this case, we're actually just using interstellar space to cool the spacecraft. So this heat shield is mechanically pretty complex. You can see it's actually a very thin membrane. That membrane is only about the thickness. There's several layers of it. They're only about the thickness of a human hair. They are coated with, on the two hotter sides, with a semiconductor coating to give enhanced reflection in the infrared, and then also to reflect visible light from the sun, which is of course going to be a major source of heating on the spacecraft. And so this heat shield, the great thing of course is once it gets deployed, it doesn't require any power, but deploying it is mechanically complex in a vacuum. The other thing to realize is this spacecraft is really made for operation in space. It's on Earth, it is incredibly delicate, because once it's out there, it doesn't have to worry about gravity. Okay. And then there is an active cryo cooler for some of the cameras, so that will bring them to an even cooler temperature. And then this is I would say the final thing that's really the riskiest here or the one that will worry people the most, is to get this mirror out here that reflects the light back into the primary instruments. So basically the light comes in, bounces off the main mirror segments, bounces off of this mirror, and then goes into the camera assembly there. And then finally the side segments of the mirror will fold in. The mirror's in pieces for one reason, is simply to be able to fold it to get in the spacecraft. But the other is, and this is a technology that's come in from ground-based telescopes, is you can put little motors on this mirror and position those segments to refine the focus of the mirror. And actually that's easier to do in space. They won't have to be moved very often. And once they're set, they can basically be left in that position. And then this final point of this video showed you a little bit about the halo orbit again. So that is the thing that is most, I would say, surprising about this telescope. Hubble Space Telescope actually was essentially all you had to do to put it in place in orbit was to unfold the solar panels and open the door. Okay, it was a much more compact design, but of course a much smaller mirror. Here are just a few things to compare them. The Hubble Mirror is a little more than 6 feet across, maybe about 7 or 8 feet across, 2.4 meters in diameter. It has an area of about 4.5 square meters. The JWST mirror is 6.5 meters across, has an area of about 25 square meters, so 5 times that of Hubble. It is looking in a different wavelength area of the spectrum. The reason it's coated with gold is the most reflective material to use for the infrared. And it's actually a very thin coating of gold. It's actually not a major part of the expense. The mirror structure itself is made out of the metal beryllium, which is very light and has very good properties for surviving extremes of heat and cold, and is very rigid. And actually, even though the mirror is 5 times greater in area, it's about, I believe, about 200 pounds lighter than the Hubble mirror. So it's a new design, much different way of constructing the mirror. As I've mentioned, the cameras are basically cooled in JWST, both by the heat shield and the some active coolers. It is in this very high orbit, as I've mentioned. The Hubble is at about 340 kilometers. That's about 180 miles above the Earth, so it was relatively easy to reach with the space shuttle. Hubble has a lifetime of possibly as many as 40 years. Basically, the state Hubble is in right now is, as long as it doesn't have any major mechanical failures, it will be able to operate for at least the next 10 or 20 years. Okay, its orbit is eventually going to decay. It's not likely to last past another 20 years from now if that's somehow maintained. The one important limitation of JWST is it has about a 10-year lifetime in that halo orbit. It will run out of maneuver fuel. The planned mission, which it was funded for, is 5 years. They have doubled the maneuver fuel budget, so it should hopefully last 10. If you look at the costs, Hubble's cost to launch, if you run it up, and this is just rough calculation, not being a financial person, but if you run it up to 2021 dollars, Hubble's to launch cost was about $3 billion. But there were a number of other repair missions and upgrades were possible of Hubble Space Telescope. And so its total cost, I think in 2018 dollars, was something like $11 billion up to about 2018. The JWST, the to launch cost, as Dr. Anwar mentioned, is pushing $10 billion. But when I was a graduate student at the Very Large Array Radio Telescope in Socorro, New Mexico, it's a big field with 27 very large antennas. I gave summer tours, and I was always asked about how expensive it was. But the thing is, I had grown up in a Navy-based town, and I knew what jet fighters cost. So I always told everyone that the entire array you see in front of you cost 5 F-14 jet fighters. So that's an important thing to realize, is the scale of budget of NASA compared to the scale of the budget of other parts of our government is actually pretty small. As I understand it, the cost overruns on the current F-35 fighter plane program are on about a scale of about $100 billion. So 10 JWST telescopes, okay? That's just one part of the budget. NASA only gets about $1 billion per year for astrophysics research. So this represents, though it is a multinational project, there are many other contributors. This is, about 10 years of NASA budget for the spacecraft so far. So just to quickly try to explain to everyone the layout. You've kind of seen the picture already. It basically has a cold side and a hot side. The heat shield, again, is designed to use multiple reflections. So primarily it reflects the sunlight off the heat shield, and then any heat that's absorbed by the outer shield is going to emit some infrared light to the next shield, which will reflect some of it out, to the next shield, which will reflect some of it out, and so forth, to really cut down on the total amount of heating that reaches the spacecraft. The spacecraft overall, when it's unfolded, is about the size of a tennis court. Okay, so that's a good kind of image to keep in mind. Here is an actual ground test deployment of the heat shield alone. You can actually see two people standing on a platform there up through the access way for the tower part of the spacecraft, and they are, examining the surface in the unfolded heat shield. Here's a comparison of the sizes of Hubble and JWST, and down here on the right are face-on view of the mirrors. I also have there's a really short animation that will show where everything is here and shows a person for scale. So there you can see the sizes of the two spacecraft. The Hubble was basically the size of the Space Shuttle cargo bay, but you can see the mirror inside here was considerably smaller. Though in some ways Hubble is in a harsher environment in that it was in lower Earth orbit. There's a little bit of drag from the atmosphere. There are occasionally minor collisions with space debris with Hubble. In many ways, JWST is going to be out in a somewhat cleaner environment when it gets out beyond the moon. But that gives you a good idea of the scale of these spacecraft. But of course, the JWST has to be packed up inside the launch canister of the Ariane 5 booster. Again, here's some images of the mirror on the ground during testing. One thing you may sometimes wonder, and if you think about what can be done if some of these steps fail. For instance, if the heat shield fails to deploy, that would be a really major problem because this telescope would be much more difficult to use. If some of the mirror segments don't unfold, that's still a problem, but it would be, we could get by with only 60% of the area or 80% of the area or something like that. There are ways to at least partially compensate for that. But the boom to come out the front with the secondary mirror is really a very critical point. I think this is I've had some pictures be a little slow to come in here. So here's one of the major deployment tests on the ground, showing most of the mirror deployment and the tower deployment and the heat shield in place. And you can see there's a typical cherry picker, can kind of give you an idea of the size. I have a friend who has been working on this project, and it's basically been his entire career, 26 years. So, now I was going to mention a few things that just from my experience, when Dr. Anwar asked me to do this, I work in a collaborative project on radio astronomy with about 40 other faculty spread out over the United States and a few people internationally, both in Puerto Rico and Spain, and we've actually collaborated with people in Australia. And we have used the internet extensively. So we do radio surveys of distant galaxies. The first survey we worked on was the Alfalfa survey, which basically looked at the entire sky that was visible with the Arecibo radio telescope from Puerto Rico, and we detected 31,500 galaxies in that band. The project took about 12 years overall. We've gathered the data for a smaller survey that's targeted called the APS survey of galaxies in the Pisces-Perseus supercluster. We're basically looking for evidence of dark matter on a new sort of scale that hasn't been examined much. We're looking to see if we can detect dark matter where a large cluster of galaxies is falling together and detect the signal of that in the gravitational motion of those galaxies. The main things I wanted to mention are, and this is, we developed after that first survey, which was our first major grant, we developed ourselves as sort of the undergraduate alfalfa team to go on to other projects, and that's what we're doing now. Now, the projects I'm involved are very small compared to the JWST scale. $1 million every few years, okay? These are mostly travel, observatory lodging, sometimes student stipends, mostly from the National Science Foundation. One thing to realize in research astronomy is that you're not charged directly for observing time on the telescope. That's considered to be part of the cost of the telescope or the general operating cost. You generally, though, if you travel, you have to pay for lodging, things like that, travel costs. I hope this. We do most of our work remotely, and this would probably happen if you were working in a large international project. We actually control the telescopes remotely a lot of the time over the internet. These are just a couple of nifty screens from controlling the Green Bank radio telescope. We started doing this long before Zoom. We would actually call up the observatory, but then we would use IP tunneling and actually control computers by remote control. You would actually see the other computer's screen on your screen, but you typically wouldn't have a camera. And that's what these images are from. Of course, now Zoom is very useful, and we were pretty early adopters. I was one of the people who had used Zoom a fair amount before the pandemic. So, just some lessons I think that are important for kind of human factors. We have collaboration of about 40 faculty and scientists, and grad students are kind of the more advanced workers. About 10 or 20 different undergraduates work with us in a number of different schools per year. We have a yearly or bi-yearly face-to-face meeting, a workshop. And I think that's very important in these kind of projects. You need a point at which a large number of your team members come together and actually meet face-to-face, even though you won't be working all the time face-to-face. It's really important for cementing your relationships, for team building, mentoring and training new members, and it's a very intensive group experience the way we do it. We get together for just a week. We make people work on the telescope right there, where there's an operator to help them, so they actually get to see the telescope work mechanically. Sorry for the little delay. I think there's some hidden pictures in this. Yes, so you also have situations where you would travel in smaller groups, maybe to different sites. This is an image of me at the Arecibo Radio Telescope about 5 years ago. You often do this in small groups. Again, these things can be pretty intense. Our observing seasons were spring and fall during the year, and we would try to have several groups of people under ideal conditions, if funding was good, actually go to the telescopes to do some of the observing, because there's nothing like doing it there. It's much more fun than observing remotely. You also understand what's going on much better if you're there at the site. You meet the people at the site that you need to call in an emergency. All those sorts of things are important in these kind of collaborative projects. And for the people that are the leaders, this is an important part of the training. I went down once with only one other senior scientist, and we spent a week doing observations, and actually it turned out to be during a period when the telescope had a mechanical failure. So we learned a lot of things about using the telescope under difficult conditions. And then I later, a few years later, did the same thing with another group of younger faculty in the collaboration. There's a missing picture here, sorry, but then there are, of course, professional conferences. There are cases where you present your results to the scientific community. You can also present your model for your team in collaboration. And it's also a more relaxed face-to-face meeting for everyone. You can socialize some at the meetings. You can do informal long-term planning. You can see what's going on in the community. You can look at what possible funding prospects are and so forth. So a typical meeting I would go to is the American Astronomical Society, which meets twice a year. There's generally one big meeting and one smaller summer meeting every year, and it's the professional society associated with the discipline. A few things we've learned about the pandemic. You never realize how important occasional travel is until you can't do it at all. When you have people that, you end up working with people you've never met, or you can't go sit around a table. Even Zoom is very amazing technology, but it's just not quite the same. There's a lot of attention you have to pay to the screen. The social interaction's pretty strained sometimes. And we have started using, just as there are very interesting online collaborative software now systems, for many of them coming from the software development community. The one we've started using is called Slack, where it's basically your own private message board, storage place. And the combination of Slack and Zoom can be pretty good for trying to maintain a collaboration when you can't meet at all. So I just thought those were interesting things we've learned, of course, on a much smaller scale. But if you think about a project that costs $10 billion, you can imagine these problems multiplied many times. So, okay, so I guess that's my little presentation. So, any questions? Thank you.
Let's open this floor for your questions. Very interesting topic.
You can ask about anything about astronomy, or yes.
So what exactly is the satellite looking for? Like, what are y'all trying to see?
A whole range of things. It would be used for studying like star-forming regions, like that gas cloud that I showed. It is possible that it will be able to detect some. It's actually likely to be able to detect some planets around other stars indirectly, or actually directly, I should say. I'll ask y'all actually a question. If you've not been in my astronomy class, and particularly further into my astronomy class, how many planets do you think that we know of outside our solar system right now? Well, actually, somebody's been reading elsewhere. It's probably maybe not 10,000 yet, but confirmed extraterrestrial planet detections are probably about 1,000. Only partially confirmed ones are up in 3,000 or 4,000, and it grows by hundreds a year. Okay, so we know that planets are common in the universe, but whenever you're looking at a planet, you're looking at a bright star. It's orbiting a star, and so a planet is a very tiny object shining by reflected light. So they're very difficult to detect directly. Right now we detect them mostly by cases where they cross between us and the star and slightly dim the light of the star, or we look at cases where we can measure the velocity of the star by shifts in very fine details of the spectral lines of the star using the Doppler effect, the same way the police stop you for driving too fast. We can measure the speed of the star relative to us. Those two ways can detect planets, but they're both somewhat indirect. And there have been almost all with infrared telescopes, a few cases where large planets orbiting far from the stars that are pretty hot can be detected by infrared telescopes. JWST is under much more ideal conditions. It's in space. It doesn't have to deal with the atmosphere. It's going to be able to push the limits of how close we can detect a planet to a star directly and how small a planet we can detect around another star by quite a big deal. The other thing is the infrared sky is almost completely different from the visible light sky. You can see lots of details of the dust and cooler stars and galaxies all across the universe. It's also designed to be able to detect galaxies as galaxies move away from us, the universe is expanding. As you look further and further back in time, as you look further and further back in space, the light is shifted toward the red and then toward the infrared. So the most distant galaxies that we can detect out almost 13 billion light years out are going to be much more visible in many ways in the infrared. And so it's designed to be a general instrument for astronomy. So it's a major observatory. And the way you would get data is you would submit a proposal to the probably NASA, probably through the Space Telescope Science Institute may be part of it. A proposal, you know, I would like so many minutes of time to look at this set of objects, and it's submitted to a peer review panel. And if you're granted the time, the telescope points at that. Probably an operator would point it from you, but you would give them the parameters of the thing you want to observe, and then they would send you the data free of charge. Okay, but that's part of the funding of the telescope is to fund basic science. And but the thing is, it has to go through a peer-reviewed proposal, and the time is extremely valuable. So there's committees of scientists that rank sets of proposals, and you know they have some sort of internal cost, but it's more of a which the cost is really time if you're looking at the scientific merit of a proposal. And so you submit for so many hours or so many minutes of telescope time to observe a particular object. I mean, the project we worked on, we were with the Arecibo Telescope, which was the largest radio telescope in the world. Our project eventually got hundreds of hours of telescope time. So it was actually one of the larger observation programs on the Arecibo Telescope in Puerto Rico. But that's the way most nearly all scientific observatories like this work. You submit a proposal to a peer-reviewed panel for a certain amount of time. And of course, before the internet, you would travel to the observatory to get your data, and you would have to foot some of those costs, or often most of those costs, the travel costs and so forth. But the internet has helped that. But again, it's still very valuable to travel to a ground-based observatory. It'd be nice if you could travel to the JWST, but that's going to be even more expensive than the JWST itself. So, okay, yes.
Do you think the lifespan of the telescope was made in mind of us possibly being able to go there before that lifespan is over to refuel and repair?
That's a possibility. I mean, that's actually the thing, one of the things to realize, NASA doesn't operate under fixed cost contracts. And success is not doing things on cost. Success is getting the scientific return. And that's essentially what happened with Hubble. There was the capability to repair it and upgrade it. The first mission to Hubble after it was launched was an emergency repair mission. But basically the other two missions afterwards were upgrades. They basically upgraded the cameras, upgraded some of the optics. This one is a bit far out, and but I do think it's interesting that they put the grapples on there. But it's sort of like, it's a possibility, but that again is dependent on future funding. I mean, any space mission costs, even a small satellite probably starts at $100 million. And you'd have to have a pretty sophisticated, if it was an automated or a remote controlled spacecraft, it would have to be a pretty sophisticated spacecraft to go and grapple with it. If you talk about a crewed mission, SpaceX is pushing the cost down, but it's still, that would be beyond the moon. That's much riskier. It would still probably be at least billions of dollars to send astronauts there, and risky. So, yes?
What are your thoughts on the private space race happening now?
Well, I'll be frank and admit I'm a big fan of what Elon Musk has been doing. I don't really think any of the other competitors they're not nearly as far along, because they do not. The thing to put something into space, the Bezos' thing, there's this idea, it was actually from an aeronautical record system, that if you got above about 60 miles altitude, you were in space. But it's not just that you get to 60 miles altitude, you have to get to really about 100 miles altitude and be moving very fast to remain in orbit. And so there is actually a whole order of magnitude difference between Musk's launchers, the Dragon, it is an completely orbit-capable spacecraft. You know, it's like it launches manned capsules that can go all the way to the space station. And if the BFR gets finished, will be the largest rocket ever built, or the biggest thrust rocket ever built. It will be taller than the Saturn V that was the moon rocket. And so, if that succeeds, it's really a whole other ball game. Actually, if you know, just to make a joke, but I wish he'd just shut up and build rockets. You know, it's like he's doing such a good job of it, or his company is. So.
So David, we are teaching, this course is international marketing, and we also teach international management, global strategy. When you work with the multinational teams, tell us more about what kind of difficulties do you people encounter in terms of sharing knowledge and getting things done?
Okay, well, the collaboration that I've worked in, we haven't had too much trouble sharing knowledge, I would say, except that, again, it really is important as a human factor to be able to come together at least some of the time to do that. I would say one of the things to realize that does happen, this is particularly in the sciences that are funded, are not profit-oriented, is that your institution or your telescope will eventually, particularly as it ages, like the Arecibo radio telescope, it gets handed from one institution to another for maintenance and management. Someone will lose a contract for maintaining the telescope. It'll get awarded to someone else. They may not do it as well, or there'll be a sudden change in the management style. And this is not something that I was as directly involved with, but I knew about the problems. Like we would suddenly have planning problems, say like getting a conference area available because all the paperwork and all the procedures would have changed. And I would say, from my experience, one of the most troublesome things is when you have a project that shifts from being built and from its first primary funding and development to sort of a maintenance mode when it's still doing something, in our case, very scientifically valuable, but it gets passed from one management group to the other a couple of times. And so that can cause problems for the users, for the people that are using that institution as a service. And of course, again, with scientifically funded projects, the argument can be made that, if y'all don't know this, I guess I should have mentioned, the Arecibo Telescope that you see, it's actually in the background in the picture with me in it. I can get this to shift back. Anyway, it collapsed during the pandemic. It had known mechanical problems, but it was, probably from many years of slightly, a little bit underfunded maintenance. And with big things like that, basically you see this window in the background, that's actually a tinted window. This is near dawn, I think, or either when I was working there. That feed structure in the back, that grid up here you see, this was actually the feed structure that hung over the dish. So the Arecibo Telescope has a huge dish in the ground about 1,000 feet across. And you can move this structure around to point the telescope within about 20 degrees of straight up. And so that gives you your range that you can cover geometrically. It was supported by 3 huge sets of cables, like cables that would be used in a suspension bridge, from 3 very large towers, concrete towers that were built in the ended in the 1960, 1958. And the cables had been upgraded, so there were actually the original cables and newer cables. It went through an earthquake, Hurricane Maria. Actually, the eye of the hurricane went directly over Arecibo. And in 2020, they'd actually acquired funding to, basically everything was stretched a little bit by the hurricane, so parts of the telescope were out of line. It was still usable, but it needed what's called a survey, and then retension all the cables, the smaller cables, and check the bigger cables. But while that work was sort of being done, they realized that one of the large cables was failing, and it actually reached the point where they evacuated any dangerous part of the site. And then in November last year, one of the cables broke and the whole thing came down. Now there's still a scientific facility there. That might be another interesting thing to think about in your class is what can you recover if you have a catastrophe at a facility? Because that 1,000-foot dish in the ground was not totally destroyed. It's still quite useful. You've got the infrastructure of all the buildings. You have a very well-trained technical people both there and off-site who worked on it. And so there is a proposal underway to rebuild it, but in a different way. It would probably be a different sort of design. And it's another telescope that served multiple purposes. It was radio astronomy, but it was also our main planetary radar for looking at asteroids passing near the Earth. It was can give you by far the best orbit information. You know, whenever an asteroid's detected and, you know, all the papers try to get everybody to panic, you know, and they say, oh, there's some chance it'll hit the Earth, and basically when Arecibo pinged it and got a radar signal and got its orbit exactly, it's like, nope, no problem. So that was and that's actually a major impetus for refunding it, is that it is very useful as a planetary radar, which also has scientific uses as well. So, all right.
Well, before we conclude, on behalf of
Oh.
college, we have a small token of
Thank you.
appreciation.
Thank you very much.
And we hope you enjoy it.
Okay, thank you.
Have a seat.
Okay,
and
yeah,
I'm
but
going
it-
to make a few comments.
All right.
Before we conclude, as always, every lecture has some purpose, and if you apply to this class, International Marketing, Global Strategy. So now you know when you deal with complex projects, you have to deal with languages, and these are my notes. You have to deal with different cultures, cultural dimensions. Teamwork is very important, and teamwork doesn't come so easily as Professor Craig mentioned. There are lots of challenges in the project, as you know, the issues you guys have. But when I look at the data, there are over 300 entities involved in the telescope. It will take 1 month to get to its point, L2, and it's going to be dealing with all the deep space. But after December 18th, make sure you keep track of all the activity, because when you deal with the complex projects, they are not going to be a few million. These are billions of dollars, and that's where you need what we call collaboration. And alliances, collaboration, and countries collaborate, companies collaborate, and sometimes it gets very complex. You know, for us, when we look at automobile, or when we look at a big project, or when you buy a product, you need to go behind the scene and see how long it took them to manufacture, and what are the issues behind research and development. So this is where we have the project, and I purposely selected this topic because of Hubble, and now Hubble will be dealing with the Webb telescope, and it will be all over the world after December 18. I hope it is possible to be redeployed, and it's going to change all the issues, and basically you are dealing with lots of revolutionary things and more knowledge. But again, as Professor Craig mentioned, there are thousands of new planets. And can you get to them? Maybe not, because each one is one light year is 5.8 trillion miles. And this is not Star Trek where you say, you see me up, Scotty, and you are there in a few minutes. Although Captain Kirk did go upstairs, but he was only for 10 minutes, and he was back. But this thing is very big. But NASA is, along with the European Space Agency and Canadian Space Agency, NASA is one of the most unique. And so this is where we conclude our session, that it's very important to understand complex projects, and they are under our discipline. But again, I would like to show you again this National Geographic. We are not alone, or maybe we are alone. But we will find out. But it's going to take a long time. Not during our lifetime, maybe beyond. Because if you look at Captain Kirk's, birth date, he was born in 2233. And if you look at the Star Trek, I was looking at this data yesterday. But thank you so much, David, and let's appreciate our good friend, David.
Oh, thank you.
Thank you again, and we'll see you next time. Goodbye.
Okay.